Okay, folks. So for our last talk of the day, Alexander's going to tell us about Fano stuff.
All right, cheers. Thanks very much. Yeah, I was going to use slides, but I can't tell you how pleased I am that the technology doesn't work in Oxford. I can't wait till I get back home and tell everyone. Okay. Thanks very much for the organizers for inviting me to give a talk. I feel a bit of the odd one out because I'm not a physicist and I'm not a machine learner and I'm barely an algebraic geometer. So goodness knows what we're going to do. I think the microphone's on. Yeah. Yeah. Yeah, I think it's on. You want me to raise the good. It's green, yeah. Ah. Well, no, but I mean, it's definitely not. Oh. Good. My mouth finished my beer. Good. Right. I'm very pleased the technology doesn't work. Okay, great. So yeah, what I want to talk about is sorry, you're gonna have to rethink this talk because it was on the slides, but it's machine learning. Can everyone see this? Okay. The Fano landscape. Okay. And this is, all of this is joint. Well, actually, funny enough, this has sort of grown out of a different project, sort of computational project in geometry. I'll say sort of this immediate thing, this idea of using machine learning. This is joined with 3 other people. So we have Tom Coates and Giuseppe Piton. Unfortunately, Giuseppe has decided to leave us to go make a lot more money in the city. And Sarah Veneziali is going to be doing the tutorial session on Friday. And there she is at the very back. So in particular, if you have any questions about what I'm going to talk about, brilliant. And so I'm going to come with a little disclaimer, which is I wasn't sure what the audience would be, whether you'd be algebraic geometers, whether you'd be physicists studying Calabi Yau, whether you'd be people just interested in machine learning. And so almost everything I say is false, okay? But it's all morally true. Okay, so what I'm aiming to do is convey some sort of idea of the big picture of what we're doing. And I'm going to try not to get bogged down on details. Of course, what's really going to happen is the bits I enjoy, I'll get bogged down on details, and the bits I don't care so much about, I'll gloss over. But I'm going to try and just keep this big picture and just try and explain some of the highlights of the mathematics of what we're going to do. And the other thing that I'm afraid, I'm going to alienate all 3 possible audiences. So the other one is, I'm afraid all the machine learning that we do is incredibly basic. I mean, embarrassingly basic. I don't even know if it really counts as machine learning. It's more just bog standard first-year undergraduate data science. But what excites me is not the fact that we're using machine learning, although the potential is massive. What's exciting is even with very basic tools, we're getting amazing results. Amazing mathematical, I suppose, results. or amazing insight into the mathematics. So that's what's really cool, in my opinion. And, you know, goodness knows what would happen if some competent people had a go at this problem. Okay, good. Where to begin? I think I'm going to begin by defining projective space. I'm also going to move the microphone out of my beard. Okay, good. So algebraic geometry. For me, I'm really interested in just a few very basic geometric spaces. They're all going to look very similar to each other, so it makes sense to just really define carefully what we mean by projection. And I've got to say, whilst I remember, everything that I do is over C. Okay, I never touch the reals, because that's far too hard. But everything is over C. And in my slides, I made a real effort to constantly write the C's. I'm not going to do that on the board. So projective space. So I want to begin with P1 for the people who aren't familiar with it. So the projective line. So we saw this in the first talk. Today, what do? So we take a copy of C2, knock out the origin, and then we impose a little equivalence relation. And that equivalence relation is just lines through the origin. So we say that x, y is equivalent to lambda x, lambda y, for all lambda star. Okay. Yeah, as we saw today, you can just think of this as lines passing through the origin. And if we sort of fix ourselves a reference line sitting here, a little copy of C, what we see, of course, is that we're going to get the entire copy of C. And then when the line is parallel to this, we're going to get, as it were, the point at infinity. Okay, projective geometry. This is exactly why projective space came into being. Okay, but another way of seeing this, as was touched on, is we can also see this as two copies of C that are glued together. Okay, and so I just impose some coordinates, x and y. Well, I've already got good. These two copies are, I suppose we've got, let's call it u x, which is all those points where x is non-zero. But this is just isomorphic to C, just divide through by x. Okay, and uy, which is going to be when y is non-zero. So you can divide through by y. We see another copy of C, and they're going to overlap in a copy of, well, they're going to overlap when x is non-zero, y is non-zero, and so this is just a little copy of C star. Okay, this being C star is important. You know, obviously this is dense in the whole space. Most points are going to have x non-zero, y non-zero, and this C star is what turns us into toric variety, which was touched on this morning too. And toric variety is going to be quite important in what we do. Okay, so I'm just going to take it slowly to begin with. What about P2? Well, it's exactly the same thing. Okay, so take C3, knock out the origin, push it out by this equivalence relation. And now, well, what's the gluing? Well, we have three copies of C squared glued together. Okay, x is non-zero, y is non-zero, and z is non-zero. And if I draw a picture of this, I mean, this is a very stylized picture, but it's going to look something like this. X is non-zero, Y is non-zero. I don't know, maybe if it'll work better. Maybe you can line it up, yeah. Yeah, exactly. You think it's exactly? Well, we'll give it a go. All right. And yeah, so this is the patch when X is non-zero, Y is non-zero, etc., etc. And here, sitting in the middle, X is non-zero, Y is non-zero, Z is non-zero. We see something that's isomorphic to a copy of X star. Okay, and again, the fact that we've got this essentially sitting dense within the whole space is what's turning this into a toric variety. They're going to be the key players in what we're doing. Okay, good. And so we've seen a few algebraic varieties just now, and in fact, these all have something in common because they're what we call Fano varieties. So we can take products, which work to exactly how you think. And obviously, there's high-dimensional analogs. There's weighted projector spaces, which were mentioned in the first talk. I'll come back to those in my second talk. So these are all examples of Fano varieties. Okay, in fact, these are all smooth Fano varieties. So, what is a Fano variety? Why do I care about Fano varieties? Well, roughly speaking, and then this is where I wish I had my slides. But roughly speaking, you can divide your varieties, your manifolds up by their measure of curvature. So we have this trichotomy. We have spaces which are positively curved. Okay, so you try and draw a triangle on this, you'll get something that has a volume bigger than the standard Euclidean area of a triangle. Okay, and these are what we call Fano varieties. We have spaces that are flat. So here, there's no curvature. These are what we call Calabi Yau. Is there a different microphone? Good. Good. Yep. Ooh. This one definitely works with a delay. All right. If there's no one on Zoom, if there's no one on Zoom, we don't need to still. Try clicking yourself as well, rather than your pocket, maybe that'll Good. All right, and then suspense is killing you. What's the third time? So, oh my God. Okay, so those that have negative curvature, and this is so hard to draw for me. No, they look something like this. Okay, and the point here is that if you try and draw the volume form on it, it's got a volume that's smaller than the Euclidean volume. So here we have varieties of general type. And as the names might suggest, you know, if you just write down a random set of equations, you're probably going to be here. Okay, and there's essentially, it really doesn't matter how you slice and dice them, what your notion of equivalence is, there's infinitely many of these. And the really nice thing is that Fano varieties, you know, as long as you have some notion of equivalence, isomorphism, birational equivalence, deformation, there's finitely many of them. Okay, and then Calabi Yau is, you know, I'm sure you're all familiar. You just don't know. Okay, it's still an open question. Are there finitely many families of Calabi Yaus or infinitely many? We don't know. Okay, so it's already nice, right? If you've got finitely many of something, it begins to get quite exciting because you want to find them all and print 3D models of them and put them in a cabinet. And it gets better because if I take a slice through the Fano, I get myself a Calabi Yau. Okay, and so this is a great way of constructing Calabi Yau manifolds. And in fact, it's one of the key ways of constructing Calabi Yau manifolds. So Kreutzer and Skarka, rather famously, in 2000, which still astonishes me that they managed to do it then, they went away and they classified a particular type of Fano varieties. The details don't matter yet, although, assuming I don't run out of time, we'll come across them again later. And they found this famous 500 million examples that'll keep getting mentioned again and again. So they found these, the important thing is these are singular Fanos, in fact, they're toric Fanos, in dimension 4. And then by taking a hyperplane slice, what you end up with is, I'm on dangerous ground here, but I'm going to say you end up with at least 30,000 Calabi Yau freefalls. Okay, this is the main way of constructing these Calabi Yau freefalls. And you've all seen the really wonderful plot of the Hodge numbers. It's this really famous plot that looks something like this. And most of the Hodge numbers are down here in the bottom, and then they carry on, and it really looks, you know, very beautiful and suggestive of some rich geometry. And so maybe you could say, you know, this Hodge plot is the first glimpse of the Calabi Yau landscape. And really, we'd like to do something similar for Fano varieties. We'd like to somehow see what the Fano landscape looks like. Okay. So one more important thing about Fano varieties is they're the natural building blocks in geometry. So there's this thing called birational geometry, where you take a variety and you make sort of small operations to them, small in an algebraic sense, in a sort of physical sense, it could be a huge change. But you make this series of small operations to them, and the end point, roughly speaking, is a Fano variety. And so in a very real sense, Fano varieties are the building blocks from which all other algebraic varieties can be studied and constructed. Okay, so they are very, very important. Okay, so what do we know about them? So we're going to restrict to the smooth Fano classification first. All right, so dimension 1 classification is straightforward. And in fact, we've already seen it. There's exactly one-dimensional Fano manifold. It's P1. Dimension 2 is much more fun. Okay, so this is due to Del Pezzo in the 1880s. Okay, and because of this, we call these Del Pezzo surfaces, not Fano surfaces. And it turns out that there's exactly 10 cases. Okay, you've seen 2 of them. So there's P1 cross P1. There's P2. And then there's the blow up. This is one of those little small birational operations I was talking about. There's the blow up in endpoints of P2, where n is less than or equal to 8. So 8, 9, 10. Good. Okay. And it turns out, you try and blow up a 9th time, it stops being smooth, or stops being Fano. I'm not sure what goes wrong. You can't do it. Okay. Well, fantastic piece of work from Del Pezzo. And then the natural question, what happens in dimension 3? So the work was originally done by Fano, which is why we call them Fano varieties. And this was in the 1930s. But I got interrupted. And then Iskowski, this is where I wish I had my slides. So it's a strange spelling because it's the Russian, something like that. And yeah. It's almost right. Iskowski, apparently, is how the transliteration is. So Iskowski made great progress in the 1970s. And then finally, Maury and Mackay, they finished the job in the 1980s. So 100 years after Del Pezzo's work on the surface case. Now, how many of you have ever made a mistake in a paper? Nobody, because we're perfect. So the wonderful thing is Maury and Mackay made a mistake. Okay, so Maury and Mackay's paper, they found that there was 104 Fano frequencies, new Fano frequencies. Okay, and then and even Maury won the Fields Medal in part for this. So people were pretty impressed. And then in the year 2000, I don't know who found it, but Maury and Mackay published a correction, and in fact, it was 105. Okay, and we can laugh, but we're pretty clever. And this is a sign of how difficult this classification is. It is not easy. The Del Pezzo classification, you can set it to a PhD student doing algebraic geometry. Even now, I mean, how many years later? 40 years later. It's still hard to do. The technology that we have hasn't made this trivial. Yeah, right. So I'm being a little bit dash because our notions of equivalence are going to converge. So for me, this is deformation equivalence. Good. So yeah, so this is still a really hard and delicate exercise in geometry, is this classification. All right, good. So that's fine. We've had 40 years. So what about dimension 4? No idea. Okay. You don't know the classification dimension 4. The techniques developed by Maury and Mackay, they just don't scale with dimension. There's this sort of gap in the interesting cases that opens up, and this gap only gets worse and worse as you go up for a dimension. So the wonderful bits of theory have been developed, but the actual classification is still something that we can't get our hands on, and we'd love to get our hands on. Okay, so I should say, of course, probably most people know about Kosher Berker. So Kosher is a PhD student in Nottingham in algebraic geometry, and he won the Fields Medal a few years ago because he managed to prove, outside of the smooth setting, finiteness of Fano varieties in all dimensions. So essentially, he says, it doesn't matter. You have to sort of bound the singularities that you're allowing, but essentially, there's always finite. Kosher won the Fields Medal for us. So it's still, a thing that attracts a lot of very, very clever people and still puzzles a lot of very, very clever people. Okay, good. So maybe 15 years ago now, a new approach was suggested arising from ideas in mirror symmetry. And this has become known as the Fano search program. And that's really what I'm telling you about today. Not sure if we spell it double N-E or M, okay? And so this is a result of work by Coates, Corti, Golisher, Galkin, myself, and also many, many excellent PhD students. Okay, and the idea here is, we take a new approach to Fano classification, and we see if the physicists can tell us anything. We take inspiration from mirror symmetry. Now, really the question is, what do we mean by mirror symmetry in this context? Mirror symmetry is a project about Calabi Yaus. We're talking about Fanos. They are different beasts despite being related. So I need to tell you what I even mean by mirror symmetry. I'm going to stick to Fano manifolds because I'm on slightly safer grounds. So let's let X be a Fano manifold. And let's say its dimension is n, just so that whenever n's appear everywhere, it makes sense. Then there's this horrific, truly horrific computational gadget called the regularized quantum period. Okay, and honestly, if you have any questions about this, don't ask me, because I have no idea how you really compute this, except in some very special cases. But this arises out of Gromov-Witten theory, and the idea, roughly speaking, is you take your variety X and you count curves on X of fixed degree. But this, of course, is quantum, so nothing is straightforward, and there's little group actions on these curves, and you have to do your counting weighted by group actions and things like that. It's just awful, okay? So it's a strange thing to want to appeal to if you think you're going to make life simpler, but it really works. So I'm going to write up its definition. Well, I'm not going to write up its definition. I'm going to write up something that approximates a definition because it's useful to see. So it's just the formal power series. And this K factorial is sort of irrelevant. It plays this role of conjecturally making everything that we see into an integer where it might have been a fraction beforehand, although it's not actually a theorem that everything is going to be an integer. And this here, it really needs to be in scale quotes, but this is counting the number of degree K orbifold curves on X. Okay. Right. Well, I said before that was hard. Unfortunately, I'm going to say this is really, really, really hard. Okay. So nobody wants to calculate this, but conjecturally anyway, this completely characterizes the geometry of X. So if you can get your hand on this somehow, and you develop a whole bunch of mathematics that doesn't yet exist, you can reconstruct X. And now you begin to see maybe what machine learning might have to do with any of this, because there's maths that we don't know how to do, but maybe machine learning can do it for us. Okay. All right, good. So that's one side. So now, sharp change of direction. I'm just going to look at a Laurent polynomial. So I'm just going to award myself a Laurent polynomial in n variables. And yeah. Yeah, absolutely. I'm being a little bit hand-waving. Yeah, so I'm going to backtrack when I said yes, it depends. No, it's okay. So my understanding, and it really isn't me saying, okay, is that the more general theory that underlies this depends on the choice of complex structure. And there's some people like Charles Doran and Andrew Harder who actually try and take that into account. But here we're somehow collapsing it down. And so we're not seeing the different complex structures that you can put on. But I'm really not an expert. So yeah, the other side of the picture is I'm going to take a Laurent polynomial, and I'm just going to associate to this what's called the classical period. And that was a power series. This is a power series. Okay, I mean, it has a different description, but I think I'm just going to keep it as a power series. It's just given by a very easily computable series of coefficients. What I'm going to do is I'm going to take f, I'm going to raise it to the power of k, and then I'm going to look at the constant term. Okay, the constant coefficient. And this is a second power series. And yes, so you know what's coming. We say that f is mirror to x if these two power series agree. And so the idea of the Fano search program is, well, maybe it's easy to find the right family of Laurent polynomials. I mean, we didn't know how, but we sort of had hints from the physicists, in particular the work of Philip Candalis. Maybe it's just a lot easier to find the correct Laurent polynomials. And actually, that would be really beautiful if it was, because Laurent polynomials are just combinatorial objects. They've got Newton polytopes and coefficients, and essentially you're just playing with combinatorics. And that's an awful lot easier doing this quantum cohomology sort of stuff. And so, yeah, maybe this is the right way of approaching the problem. But how do we find them? Okay. Let me do you an example. Yeah. There's a whole tower of conjectures. So if you're interested, it's not even proven that two Fano varieties that are distinct have distinct period sequences. Okay, and it's not shown that for every valid period sequence there exists a mirror. But there's a lot of evidence that says yes, this is going to be true.
Sorry, so for Calabi Yau mirror symmetry, there's a simple relationship between the Hodge numbers. Is there any induced implications for Hodge numbers from these?
No, obviously. Really horrible things. But so there's work by people like Ed Siegel in London, where they try to really sort of categorify this and make it into real mathematics, and then hopefully prove that these things are true. Yeah. No. All right, so an example, one of the few cases where we can compute the quantum period without too much fuss. So it's thanks to a technique by Giventhal and Horivatha. Okay. I'm not going to tell you the technique. I'm just going to simply tell you it exists. And it exists in the case where we have a smooth, well, it exists in the nice case where you have a complete intersection in a smooth toric Fano variety. Particularly, it works for P2. So I can take x is equal to P2, and I have g hat x, and this is just going to be given by this sum. And I just want to point some things out in a second because it's kind of nice. 3k factorial over k factorial, so 3t to the 3. Okay, good. It's not completely mysterious. The numbers that appear in this expression do have meaning. So P2 has got, maybe this makes no sense to anybody, but if it does, this is good. P2 has Fano index 3. And that's what this 3 and this 3. Okay. And P2, you know, it's got 3 torus invariant divisors, D1, D2, D3, acting each with weight 1. And that's what these 3 copies A factorial are. Okay. So for example, if we wanted to do the same calculation for, say, P112, well, that's got Fano index 4. So we'd see 4 factorial and 4 factorial here. And then downstairs, we'd see k factorial, 2k factorial. So there's a very nice combinatorial way of calculating this in this nice completing section in the toric variety case, thanks to Giventhal and Horrigan. Good. Now, out of nowhere, but in fact, out of some papers by Philip Candelas, consider this. Okay. So this Laurent polynomial, I don't know how well you can see this, but if you try and think of taking powers and when's the constant term non-zero and when's it non-zero, that's only going to happen with multiples of 3. Okay, and what you end up with is the same thing. Except in this case, I find it a bit easier to convince myself it's true by writing it as a multinomial. So this is equal to this. So F is a mirror for P2. Okay, you're okay. So I'm gonna make one observation and park it. I'm going to say, notice that the Newton polytope of F is given by, okay, so here's my copy of Z squared. What have we got? Well, X, so that's here, Y is here, 1 over X, Y is here, constant is there. So the Newton polytope is this triangle, okay? Now, this may or may not mean anything to you, but in a second, hopefully, it'll mean something. So I'm just going to park that now. Now I'm going to tell you about toric geometry. Okay. I don't know what, sorry. Oh, sorry, yeah, it's here. So you take F, you take successive powers and read off the constant term. Yeah, so yeah, the coefficient of t to the 0 is 1. Yeah, I tell you what, shall I write them out? Yeah. I'll write it here. So it's 1 plus 6 t to the 3 plus 90 t to the 6 plus some more stuff. So yeah, so F to the 0 is 1. Okay, so that's that one. Okay, now F has got no constant term, so there's no coefficient for t. F squared, and there's no way of getting a constant term because we need to multiply. We need, the only way to get a constant term basically is to be killing this. Yes, you can't do that with f squared. F to the 3 is the first time we can score this, right? Because that times that is the times this is going to kill it. But then there's a choice of ways in which you can do that, which is exactly what this multinomial. Yeah, and actually this gives me a nice opportunity to say, you know, we've got this power series, you can think of it as a vector, right? A vector of integers. So of course, we're really working with stuff that machine learning is going to be happy with. Okay, yeah, toroid geometry, and then I probably have to close. So what toroid geometry is, it's a way of describing the gluing of the affine patches of an algebraic variety in a combinatorial way. Yes. No, F is just the Rob polynomial. Yeah. We're not trying to end out with any geometric meaning at all. Yeah. It's completely different. Yeah, absolutely completely different. We don't have this equivalence of categories on each side. It really is this, you know, at least in this concrete setting, it's this strange thing. We've got Fano varieties on one side and just families of the Rob polynomials on the other side. But there is, of course, more to the story. But yeah. So this allows us to describe a gluing in a combinatorial way. Okay, so you know, warning, and it's kind of important for what we're doing. Not every Fano variety is a toric variety. Not every algebraic variety is a toric variety. But you know, even so, we don't worry for now. Okay. So what do I mean by this? So we start with a fan. A fan is just a collection of cones. So here's a picture of a fan in two-dimensional space. Okay, and it's got 3 top-dimensional cones. Okay, and I'm going to stick the origin here. Now, how it sits in the space is important, but I'm just going to gloss over that. If you want to read more about varieties, there's plenty of good introductory texts. But the key thing is there's a fan, which is a collection of top-dimensional cones like this, and how they relate to each other is basically telling us the gluing. So in this particular case, each of these cones corresponds to a copy of C star. Okay, and these 2 cones are adjacent to each other with this common ray, a one-dimensional cone, and this tells us how they glue together. And again, these 2 glue together, these 2 glue together, and then all 3 of them glue together because of the existence of the origin. And I don't know which board it's on. It's on this one, I think. Is it? Are you giving up too soon? Yes. There we are. There's a lot of boards. Okay. That picture and that picture are the same. Okay. So we've got the 3 charts there for P2, and here we've got the 3 charts here. And this is a combinatorial description of P2 as a toric variety. Okay. And I just want to do 2 more just to sort of show you some of the beauty of toric geometry. So what's P1 look like? Well, if you think about P1, it's a copy of X and a copy of 1 over X, and they're going to glue together, and X is non-zero. Okay, that wasn't very well expressed. So it looks like this. So here's a copy of C. Here's a copy of C, and they're sort of going to glue together at this common bit in the middle. And then this is where it gets fun. What's P1 cross P1? Well, you can think about this sensibly. It's going to have 4 affine charts, and they're going to glue like this and this and this. But actually, toric geometry comes to the rescue. It says, look, take your copy of P1, increase the dimension, and just stick it in orthogonal. And here we are. It's got 3 copies of C squared. And if you think about this for a second, you'll see that, yeah, this actually agrees with your intuition of what P1 cross P1 should look like. Okay. Of course, there's details, but I'm really trying to gloss over them. Okay, now one of the details is that all of these, how they sit in R2 or how they sit in R2 with the integers distinguished is kind of important. So I'm just going to mark on a little bit of the lattice z squared. And similarly here, sitting inside the whole thing is a copy of z. And here, sitting inside the whole thing is a copy of z squared. And the details of this do matter. Okay? And you start to think about this and this are basically the same thing. I look along each ray and I see the first generator. I take their convex hull and I get that. And similarly, you know, take P1 cross, it's a little bit tautological with P1. I get this line segment. P1 cross P1. I'm going to get. Okay, and so you may say, well, whoopee-doo, of course you were going to get a mirror for P2 because you've got P2 as a toric variety somehow encoded in this mirror, and you're right. Okay, you know, I'm not cheating. That's kind of the power of this. So the wonderful thing is, even when it's not a toric variety, something similar happens and we end up with a toric variety. And so the power of this mirror construction is it's moving us from the world of algebraic geometry to combinatorics, and it's providing us with these signatures, these sequences of integers that codify our algebraic variety somehow. Okay. So next thing I want to introduce is Fano polytopes. And trying to make everything progressively simpler and simpler and simpler. So the further, in my mind, we move towards the world of combinatorics, the simpler everything is, the more tractable it is, and the more that we can work with it. So Fano polytopes is just a way of describing these polytopes that we see that give us a fan that describes a Fano toric variety. So we have that P is a lattice polytope. So in other words, the vertices are lattice points, you know, line z squared or whatever, such that 0, the origin, is in the strict interior of P, and each of the vertices is a primitive lattice point. And these correspond exactly to the fans of toric Fano varieties. Okay, and you know, just look here. So I've awarded myself some lattice polytope. The origin has to be strictly in the interior because I need the fan to be complete to cover the whole space. And the vertices have to be primitive, essentially because they're supposed to correspond to the primitive generator of each ray. Okay, and then this completely defines the cone structure of the fan, and I recover a toric Fano variety. And you can relax various conditions there. Like, I don't need these to be primitive, then you move into the world of toric stacks. But by keeping them primitive, you keep this as just honest to goodness toric varieties. And these are the sort of things people like to classify. Okay? People love to classify different sorts of Fano polytopes. And the Fano polytope that I think most of you are familiar with are reflexive polytopes. And so what's a reflexive polytope? Well, we take a Fano polytope. And we dualize it. I'll give you the definition of the dual in a second, but we want the dual to also be a Fano polytope. Okay, and the dual is just simply the set of points such that when you take the dot product with the points in P, it's always greater than or equal to -1. Okay, so in general, this is a rational polytope, but in the special case, it would be reflexive. This is a lattice polytope, and it's a Fano polytope. And this is the key player in the Batty-Rev construction of mirror symmetry. Okay, and I mean, there are infinitely many of these, but there's only finitely many reflexive polytopes in each dimension. And so again, it makes sense to go away and classify them and see what you can say. So the classification is pretty cool. So in dimension 1, there's what corresponds to P1. Dimension 2, there's 16 of them. So this is due to Batty-Rev in the 80s, I think. Okay, so you can easily Google for these. It's nice to see them. They're kind of beautiful. But essentially, in 2 dimensions, these just correspond to those polytopes that have only one interior lattice point. Well, that doesn't generalize. Okay. And then in dimension 3, there's 4,000 and something of them. Yep, so there's 4,319 of them. And this is due to Kreutzer and Skarka in, I think, 98. And then dimension 4, we've already seen these. There's 500 million of them. So the growth rate of these is pretty horrific. And again, this is Kreutzer Skarka in 2000. Okay, and in dimension 5, pretty obviously, it's not, well, there's 2 things. The theory doesn't quite exist to be able to talk about the dimension 5 classification. Completeness is an issue. But also there's very little point actually producing the classification in dimension 5. I mean, it's cool and interesting, but it will be far more than, we can't even work with this, you know, let alone what the dimension 5 is. But I'm just going to say that, that Ellie and who else? Ellie and Ed and Yang and Andrea and Vishnu, they have had some fun in dimension 5, writing a genetic algorithm that pinpoints properties of the polytopes that they're interested in and then produces partial classifications. So that's an interesting way of approaching a high dimensional thing. Okay. Why have I introduced these? Because in a way that I'll show next time, because I'm out of time, reflexive polytopes are a good hunting ground for mirrors. Right. I've got a couple of minutes. I just want to say what I mean by this. We might have lost track of the game because we've had so many simplifications. We want to classify Fano varieties. We're going to try and classify Fano varieties by their period sequence. We want to try and classify period sequences via Laurent polynomials. Okay. How are we going to find the right Laurent polynomials? We're not completely sure, but experiments suggest that you take the Newton polytope of your Laurent polynomial. It's often a reflexive polytope. Find some cunning technique for putting coefficients back on that reflexive polytope, and you found the Fano. You found your period sequence.
Somehow this was 319 will give rise to 105.
Yes, not quite. So I'll do that at the very beginning because I'm out of time, but at the very beginning of tomorrow. So, but yeah, foreshadowing, you don't quite get all of them. And there's a good reason why not. And part of that reason is because this is a mathematically correct category of objects to work with for this question. but they happen to be the things that we have, and that's all right for now. Okay. So yeah, but yeah, no, you get 98, which is actually the correct number that you expect. Good. So yeah, to say where the machine learning comes into all of this, basically machine learning in the space of polytopes, machine learning about what we can say about the geometry of X once we've got these period sequences. So it's a nice blend of big data, if you're looking at numbers like this, you know, and then machine learning to make sense of the structure of what you see. Okay, good. Right. Sorry, I ran out of time.
Thank you. Could you comment on how you go from the fan diagram to the actual variety? Because, for example, with the P2, if you just naively, if you just naively glue along those three lines, then you get something non-compact, right? So, in what sense are you gluing those three C2s along those lines?
So I didn't want to go into the sort of technical construction, but no, it's fine. So this is a cone, and you need to dualize the cone, and then you look at the semigroup structure, okay, and that's telling you the coordinate ring on that patch, okay, and because you're working over a common lattice, the gluings are explicit, okay, and so you literally see by the semigroup generators how the different patches are gluing together. So I'm not going to actually do this correctly, but you know, here's the fan. So for each cone in turn, what you need to look at is the dual cone. So I'm going to do just sigma 2 because sigma 1 is logically quite tautological. So the dual cone is kind of what you expect. So it looks something like this. Okay, and this is where the lattice really comes into play, because you see now, you know, think of this as a semigroup. It's generated by these two generators, and then I can express this one as, say, 1 over y, and I can express this one as x over y, and ditto for this cone, ditto for this cone, and then we see how it all goes together.
So you've given some examples of Fano varieties, but I think I've missed the definition if you have given it. Have you defined what Fano varieties are? Because
I tried to say that these are the positively curved varieties, so that the actual definition is these are people for whom the anticanonical divisor is ample.
Okay, and then a bit of an annoying question, but so why do you care about Fano varieties? So is it only that you care about them because if you intersect them, you can get a Calabi Yau manifold, or
no,
there...
that's just for you guys, okay? I can't care less. No, the real reason is, let's assume that you care about algebraic geometry. Okay. Then you care about understanding geometric spaces and decomposing them into simpler geometric spaces where you can actually hope to understand the mathematics of what's going on. The minimal model program takes a projective variety and simplifies it down to a Fano variety, okay, by a series of sort of controlled birational operations. And so if you can understand Fano varieties, then you know, magic, you can understand all algebraic varieties. I mean, there is another and perhaps honest answer to this. The honest answer for me, which is there's finitely many of them, and not too many of them. And as soon as you see something like that, you want to know what they all are, just out of curiosity. You know, like a sort of Victorian rich scientist who likes to create their little cabinet of all the things. I was only half joking when I said, you want to create 3D models of them all and put them in your cabinet. I want to do the equivalent thing.
Right, thanks.
Yes, that's something I want to do right at the beginning of tomorrow.